Good afternoon, everyone. Today, I would like to talk about symmetry protected topological phases in quantum integer spin chains from Tsinghua University in Beijing. The outline of my talk is the following. First, I would like to briefly review the Haldane gap phase and the AKLT state in quantum spin 1 chains. And then I would like to consider the generalized AKLT states for the higher integer spin chains. And next, I would like to present all generalization for high integer spin chains with a high symmetry. So the first part, I would like to give some brief review on the Haldane gap phase and AKLT states in quantum spin 1 chains. For the antiferromagnetic quantum Heisenberg spin chains, as it's well known, for spin 1/2 case, this model can be exactly solved by the beta answers methods, and the result tell us the ground states are non-degenerate, and the excitation is a gapless, and spin-spin correlation functions of all law. However, for this simple spin chain model, when the S larger than 1/2, there's no exact solution. In the early 1980s, Duncan Haldane considered this model in the large S limits. He derived a low energy effective Lagrangian in terms of the near vector of this quantum spin. And this is the form of the effective low energy Lagrangian. In this Lagrangian, there's a topological term. According to this topological term, whether it's a presence, non-presence, absence, and there are two different type of ground state one can obtain. First is for the integer spin chains, the ground state is non-degenerate, and but the low energy excitation is a gap, the spin-spin correlation function exponential decay. However, for the half-old integer spin, this topological term is present and make the ground state becomes gapless. After that experiment found a material for even for spin equal to 1 material, this material, and the neutral scattering experiment discovered there's a gap in the spin excitation. It indicates this conjecture is valid even for the spin equal to 1. And on the other hand, the numerical methods can also be exact calculate this Haldane. This is a Heisenberg model. You see the spin gap as a function of the length of the spin of the chain. For spin 1/2 case, the spin gap is converted to the 0 as the length goes to thermodynamic limit. However, for the spin 1 case, the spin gap is saturated. So people want to know for the integer spin chain what the real nature of the ground states. So in the 1988, Affleck, Kennedy, Lieb, and Tasaki consider such kind of Heisenberg spin models. So for this particular form of the model, they can exact solved. The strategies of their solution is the following. They divide this integer spin 1 spin 1 operator into 2 spin 1/2. And on the single side, this spin 1/2 states are represented by alpha beta states. And on a single side, this state are projected onto a spin triplet. However, for the nearest neighbor sides, the 2 spin 1/2 form a singlet. And so they can form such kind of valence bound solid states. For such kind of state, you can write down the ground state wave function in this form. When you can also re-express the matrix elements, this A in terms of some matrix form. So this is the so-called matrix products ground state wave function. And the 2x2 matrix are given by this three 2x2 matrix. And after having this ground state wave function, they can calculate the spin-spin correlation function and find a finite spin correlation length. However, when people look at the spin configuration in the ground states, you can clearly find there's a hidden antiferromagnetic order in this spin configuration if you don't count the spin SD equal spin SD 0 states. So the spin -1 +1 alternatively appear. In order to describe this hidden antiferromagnetic order, and when people propose such kind of non-local string order parameter, and this non-local order parameter has a finite value in the thermodynamic limit. And also, if you have an open boundary chains, so at the end of the chain, there are 2 nearly free spin 1/2 H spin. And this is the main feature of the AKLT states. Moreover, people also found a unitary, non-local unitary transformation. When one apply this transformation to the spin configuration, so according to the spin orientation of the H spins, actually this transformation flip all the up spin to the down spin to the up spin, and the resulting states is a diluted ferromagnetic states. Clearly, this is a long-range order states because there's a finite spin magnetization. And when one apply that non-local unitary transformation to the Heisenberg spin-spin correlation, you can notice that the original spin SU2 invariance is broken down to a Z2 cross Z2 symmetry. So, and in this new representation, the non-local string order parameter becomes a local one. It's just a local spin-spin correlation function, which describe that's a transformed diluted magnetic ferromagnetic states. So this result is obtained at that special coupling special form of the Hamiltonian. However, one can also consider this bilinear backtrotic Hamiltonian, and clearly there's a range of there's a phase in the ground state phase diagram there's a parameter range in this phase diagram. In this whole phase, somehow the property obtained at the AKLT point actually are valid in this whole phase. That is the finite gap in the spin excitation, and the finite spin string order parameter, and the unique ground state for periodic spin chain, and nearly fourfold degenerate for the open spin chain. So in this sense, we can regard it as this AKLT exactly solvable point as a fixed point model Hamiltonian of the whole Haldane gap phase. So this, however, what about this generic features for the higher integer spin chain? The easiest things, let's just consider the generalized AKLT states for the higher integer spin. If we follow the strategy of the AKLT methods, let's consider spin 2 chains. So we divided the spin 2 atom into a 2 spin 1 operator. So this 2 spin 1 can be formed total spin 0, 1, 2. So we project this 2 spin 1 states on same side, on single side, into a spin 2 states. The nearest neighbor spin 1 states into a singlet states. So so one can still get this valence, the generalized valence bound solid states. And also one can write down the parent Hamiltonian, which expressed in terms is P3 and P4. What the meaning of this projection operator onto this total physical spin channel? Let's, for example, if you consider two spin 2 atoms nearest neighbor, and in total you can have a total spin channel 0, 1, 2, 3, 4. But when you construct the ground state like this one, and you just left the 2 spin 1 at the edge, and so the total spin 3 and 4 doesn't appear. So just give you this parent Hamiltonian. For such kind of states, you can also get for the following result. For the periodic boundary condition, the ground state is unique and have with finite correlation length. There's a gap. For the open boundary condition, one can have a 9-4 degenerate ground state. However, in this in the spin configuration for such kind of states, one don't have, one cannot find a hidden antiferromagnetic like long-range order, or no non-local string order parameter. So what's happening to this spin 2 VBS states? Let's so I would like to point out there are some consideration related to the spin representation. If we carefully consider the physical spin, which is transformed in half-odd integer spin representation, then the description of the SU2 symmetry group is acting faithfully. However, if we consider if the physical spin transform in integer spin representation, this SU2 representation does not act faithfully. The actual symmetry should be SO3. SO3 is the SU2 quotient Z2. So moreover, this SU2 group is completely different from the SO3 because SU2 is a simply connected Lie group. However, while the SO3 is a non-simply connected, and also the SU2 and the SO3 are although are identical, but they differ in their global topology. In particular, we would like to point out this SU2 is a projective representation of this SO3 group. For this generalized AKLT spin 2 chain, its H spin is spin 1, so which is not the half odd integer spin representation like in the spin 1 chain case. So according to the theorem proved by the Professor Wen and his collaborator in this two paper, for such kind of, if the H spin is not the projective spin representation, the degenerate H states are not protected by symmetry, and which this state may be adiabatically connected to trivial band gap states. So for the integer spin chain, if we just adopt the construction methods proposed by AKLT, it seems to us there are two different types of generalized AKLT state, this spin gap, integer spin gap states. First is this old integer spin AKLT gap phase, which has old half integer H spins. And these H spins are symmetry protected. So this state is topological non-trivial. And the second is the even integer spin AKLT gap phase. Since its H spin is integer, so that states are not that H states are not symmetry protected. The corresponding states is connected to the trivial states. So, so in this sense, for the general quantum spin chain, there are three different families of ground states. One is this for the spin half-odd integer. And for the spin integer chain, there are also two different family states. And in order to deeply understand the difference between the odd integer spin gap phase and the even integer gap states, and recently we consider the following problem. As you may notice that for the spin 1, for the general bilinear biquadratic spin 1 models, there's a quantum critical point. It's sitting on the theta equal to minus pi over 4. This critical point separates two gap phases. One is the dimerized phase, another is the Haldane gap phase. If you regarded this dimerized phase as a topological trivial gap phase, and Haldane gap phase is non-trivial. So this critical point is very important because we can develop an effective field theory around this critical point to understand the nature of Haldane gap phase and this trivial gap phase. So recently we generalize this, certainly there's a critical point. So we generalize this idea to the higher integer spin problem. We consider this beta ansatz integrable Heisenberg antiferromagnetic spin chain model. Is a little bit complicated, but this model is exactly solvable by beta ansatz, which just correspond to the critical point of, in the spin 1 case, just correspond this point. In the in this high integer spin, it corresponds to this critical point separate the AKLT gap phase and the trivial dimerized phase. So we found actually we can decode the topological information from the effective field theory, because we noticed that for the general integer spin S chain, the S is integer, the quantum critical theory is characterized by the SO3 level S West-Wheaton models. And depending on the parity of the spin, this effective field theory actually is divided into two distinct universality class, and the low energy excitation are great different for the even integer spin case and the odd integer spin case. And for the odd integer spin case, the gapless excitation, including bosonic excitation and fermionic excitation. However, for the even integer spin case, there's only bosonic gapless excitation occur. And moreover, this quantum critical integer spin chain model also corresponding to two-dimensional topological order phases, which can be described by SO3 double topological Chern-Simons theory and topological spin theory, respectively. Due to the time limit, I don't go to detail to introduce this the detailed contents. So next, I would like to introduce you another generalization of the non-trivial, topological non-trivial states for the high integer spin chain with high symmetry. Actually, let's come back to consider spin 2 chain case. Actually, we can divide the spin 2 operator into two spin 3/2 fermion. So, and then following to construct this valence bond solid states. So in this case, we regarded the auxiliary particle as a spin 3/2 fermion. So when you combine this two spin 3/2, the total spin 1 and 3 channel are permitted due to the Pauli exclusion principle. The only possible total spin channel is spin 0 and 2. So we project the total spin state onto spin 2 states, and each there's a 2 spin 3/2 fermion on the nearest neighbor sides form a singlet. So we can write down the ground state wave function in this form. And this ground state wave function can also be represented as a matrix product states. However, in this case, this matrix is a 4x4 matrix given as the following. So, and moreover, as you can see, in these states, the H spin is a spin 3/2, which is a projective representation. So these states has a non-trivial topological structure in it. For this state, we can also find the parent Hamiltonian in this, which is given by the P2 and the P4 instead of P3 plus P4 in the generalized AKLT case. So the property of the ground state for this new gap states are the following. For the periodic boundary condition, the ground state is unique and with a finite correlation length. For the open boundary chain, we have a 16-fold nearly degenerate ground state. And we can find a hidden antiferromagnetic order and also non-local string order parameter for in this ground state. However, there's an additional property we have to consider, which is in this particular ground states, we find there's enlarged SO5 symmetry emerged in the ground state wave function, although the Hamiltonian, the parent Hamiltonian, doesn't have the SO5 symmetry. So we can how does this SO5 symmetry emerge? Let's just look at the generalized one-band Hubbard model for spin 3/2 cold fermion on optical lattice. So we consider this model in 2006 with Professor Yu and my PhD student, former PhD students. So for this model, due to the fermion has a hyperfine spin 3/2, so for each size, the number of states can be occupied by 4 fermion. If we consider half filling, the number of fermion as 2. And also in this problem, you can see there are two interactions. One is this density interaction. Another is this spin-dependent interaction term. So the ground states, the nature of the ground state is highly dependent on the sign of this spin-dependent coupling. When this coupling C2 is negative, so on the single sides, the states will be spin 2 states. So and also for this particular form of the interaction, you can prove that there's a generic SO5 symmetry display without any fine-tuning of the coupling parameter. This point also pointed out earlier by the Chongjun Wu and the Shoucheng Zhang's group. And we can we also argue that in the strong coupling limit, you can do the canonical transformation, and an effective modal Hamiltonian for a spin 2 chain can be derived. The form of the Hamiltonian is similar as we point out earlier, this set of form. And so in this way, we can use this SO5 representation to help us to describe the ground state property of this non-trivial gap phase. So in general, for the SO5 Lie algebra, we have this commutation relation, and the important things is for this representation, we have two quantum generator which can be used to describe the spin 2 states. So if we use this two quantum number m1, m2 to describe this spin 2 state, there's a relation. It's this form. However, there's a local constraint, which means on each side, the quantum number m1, m2 cannot be non-zero at the same time. So using this representation, we can characterize the ground state, the spin configuration of the ground state for this non-trivial gap phase in terms two sets of spin configuration. Each one corresponds to each quantum generator. So if you look at this spin configuration on each set, you can see for each set, the spin configuration very similar to the spin 1 configuration in the ground state. And the other sets also the same. However, we have to obey there's a local constraint. So this SO5 emerged symmetry help us to characterize this state, the ground state. So we can find this non-local the generalized non-local unitary transformation to transform these two sets of disordered states into diluted antiferromagnetic states, and then we also find in the spin 2 case there's a non-local unitary transformation, which gave us a hidden discrete symmetry, the C2 cross E2 square discrete symmetry, and the string order parameter becomes a local one in the same similar way as the spin 1 case, and also we, as before, we can consider the generalized model and expect and evaluate the ground state phase diagram. You see, in this case, there's also a range of the parameter in the phase diagram, and the exact solvable point also sitting inside this phase, and the boundary of this phase are two quantum critical points, and in the whole phase share the generic property obtained at the exact solvable point. So, and we can continue such kind of generalization to consider higher integer spin. So we start from the SOS symmetric spin S chain, and you see for this SO2S+1 symmetry group, we have a spinor representation as a projective representation, and we also have a vector representation. So we can carefully work out the algebra to construct the parent Hamiltonian and ground state wave function in terms of this gamma matrix, and also we can write down the non-local string order parameter in the general case. So finally, let me mention our recent progress. As last year, Professor Xiao Gang-Wen and his collaborator point out an important result in the topological symmetry protected topological order phase. It says that for general quantum spin chain, which are invariant and continuous on-site symmetry group, the non-trivial gap phase are classified by the second group cohomology. And in our case, we can, if we take the general symmetry, the ground state symmetry as SO2n plus 1 to calculate this second group cohomology, which gave us Z2, which means there are only two types of gap phase, including the trivial one. So we already get the non-trivial one. So this result is consistent with strongly support our result. However, moreover, if you consider the quantum spin chain with SO2n case, there are no SPT phase without breaking translation symmetry. However, if you quotient the quotient by the 2, you can get four different number of gap phase in this case. So finally, let me make a conclusion. First, I brief review the Howland gap phase for spin 1 chain, which is a spin protected topological phase. Second, I talk about the generalized AKLT states, which can be divided by two different gap phase. One is the old integer case, which is non-trivial, and the even integer, which is trivial state. And third, I introduced you all an alternative generalization for the higher integer spin model, which have a larger symmetry. This generalization can be worked out for any integer spin. So thank you for your attention.
Questions?
Yeah, clarification. I just want to make sure that I understand precisely the meaning of this SO5 spin chain. Can you go back to the picture where you show the construction of the string order parameter in pictures? Yeah, I guess that is.
Is that this?
Yeah, and the previous one perhaps.
Yeah.
Perhaps this one already flies. So the construction is basically like you start out with spin 2.
Yes.
And in spin 2 you have 5 microscopic states, 2, 1, 0, minus 1, minus
Yes.
2.
Yes.
Then you make all possible operators out of that.
Yes.
You have an SU5, you project,
Yes.
and you find out that you have a net SO5 symmetric left over. Right? That's the construction. I just want to read these pictures. So what is the meaning of a 0? The blue arrow up, the blue arrow down, and the same for the red arrows. What are they? So for spin 1 it's simple, right? It's 1, 0, minus 1.
Yes, 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 here.
Oh, here it is.
Yes.
Right, so you, wait a moment.
Here,
Yeah, you have the
there's a
two.
relation between.
Right, this
Yeah.
now you are in the SO5,
Yeah.
irreducible representation, and you have the Casimirs,
Yeah,
and it's like M1, M2, oh yes, and you have only these in the Gaussian manifold. Okay, can you go to the next one? And now you say there's a constraint, right? That when you have in M1 A0, then you are allowed to do an M2
Yeah.
A spin, right? And then you have in both of them, so they exclude each other.
Yes, yes.
And then in both of them you have this
That's right.
AKLT.
That's right.
Thank you. Thank
That's
you.
right.
More questions? If no further questions, let's thank Professor Zhang.